Let me start by thanking the organizer for giving me this opportunity to present my work here. What I wanted to discuss is the present status of this 21 centimeter signal observations and what we have learned so far. So I will skip the basic introduction of this probe because that was already been discussed yesterday, and we'll directly start with this light cone of differential brightness temperature. Now, this is a simulated light cone. X-axis is the redshift, y-axis is the angular direction. And this is created using this 1D radio transfer code Grizzly, which I had written during my PhD. Now, you see the features, all these combinations of positive and negative regions, and also the positive and zero signal regions. These are due to the presence of sources, and three radiations are mostly important when we talk about this 21 centimeter signal. Those are lambda alpha photon and X-ray photons and UV photons, right? So why this particular probe is very interesting and important is because this is a line emission, means whatever region in redshift we want to observe, these are some way connected to our redshift observation. You just choose your frequency of your observation. You just choose your frequency, and that will probe what exactly state of universe you want to probe, right? Already several observations are going on, and LOFAR, MWA, HERA are producing results. NENOFAR, it is probing a little bit high redshift, but still it is producing interesting result. ARTFAC is stopped now, and SK will come very soon. Now, these are interferometric observation. That means they are trying to probe the fluctuations of this signal as a function of linear different length scales, right? Of course, this thing we have listened yesterday as well, that this particular probe is very challenging as the strength of this signal is very small compared to the astrophysical foregrounds, and it's very difficult to basically extract the signal from this hugely foreground dominated map, which we will finally observe using our radio observations. There are also complications from instrument side, but if we are doing our calibration methods like very accurately, and if we prepare our foreground mitigation process very perfectly, then if we go for a long integration time, then it is possible to basically recover the signal which we are looking for, and this is like the hope, and this is basically the point what all the observations are taking and doing this observation. Now on, I will be basically talking about this LOFAR. This is for an example. Let's say this is a radio interferometer trying to observe this NCF field. So what they observe is this visibility in radio data, and they choose different frequency band, and this is a typical pipeline they follow for processing their data. Now they basically remove the IFIs, they do calibrations, prepare a sky model to basically mitigate the point sources and extended radio sources from their data, do some averaging, then they subtract the diffuse foreground part using, they apply a GPR based method and recover the signal plus noise and prepare the power spectrum of this signal. Now this team LOFAR, they are trying to basically mitigate the foregrounds, they are not using the OH. For example, like Samir yesterday talked about this applying the UR-OH to recovering the signal, but this team particularly is trying to basically mitigate the foregrounds and recover the signal. Now you see that this is after they do the direction dependent calibration. In this map they have signal, noise and diffuse foreground part, where you see that this red region is like strong foreground contribution. Then they apply this GPR based foreground mitigation method and derive up to this level of signal plus noise. For an ideal case, this is supposed to be a signal plus noise thing, but there are still some systematic left, and as you can see that some region the signal to this ratio is above 1, which is saying that still some systematics are left, but what the point is that for this particular plot I am showing the recent LOFAR results at 3 redshift bin. Like this is at say 10, 9, and 8, and they are prepared the upper limits on the differential brightness temperature dimensionless power spectra using this 140 hours of observation. These are upper limits that we have to keep in mind. These are not detection, means the signal is somewhere below this value, right? So here, whatever like the fluctuation levels are, these are signal plus noise and let's say remaining some systematic. Now, the thing is whether these upper limits are still useful to get some information about UR or not. So, if I state the current status of this field, that is highlighted by this particular figure, x-axis is the redshift, and there are so many observations are already putting upper limits. This dotted and dashed curves are the let's say theoretical predictions for standard scenarios, and the upper limits are here. You can see that the best upper limit is from this Hera observation. LOFAR is also producing very good upper limits at redshift 9 and 10. At high redshift, NanoFAR is also being very promising, and their upper limits are going down day by day. Only the thing is like they have to integrate, like all these observations have to integrate more observation hour to reach to this level. There at some point there will be saturation, and some this observation will claim for an detection. So these are like the status from this interferometer based observations. Now the point is like, okay, still with these observations or upper limits, we can rule out some model or not. What we learn about the UR. So this is the context of this talk. So when I am talking about inference, two things are mostly focused. One is like the properties of sources, because the signal, the strength of signal is mostly, let's say, determined by what type of sources are there, how many sources are there in that particular region which we are probing. So this particular source property inference is most of the focus of many teams. In addition to this, I also try to focus on this IEM properties, means like if I am not that much interested in the source properties, but just ask this question, how big these ionized regions are, right? I am just avoiding the question like, okay, what is the emissivity, but just I am interested in the size of these ionized regions. So these are something related to the intergalactic medium properties. Now a typical inference framework looks like this. So we use a code here, like for this LOFAR team, we use this Grizzly code, which I just discussed previously. That is working under like this source parameter, which are ionization efficiency, minimum mass of UV emitting halos, minimum mass of X-ray emitting halos, and X-ray efficiency. Now, for a combination of this parameter, Grizzly will produce a map like this, right? For that, we will produce the observable. In this term, these are the power spectra, and then we will basically couple that with the observed one through a likelihood. And this is a basically Bayesian framework which we use. Now, as I am also interested in the IEM quantities, so I also consider these parameters which are related to the intergalactic medium properties, which are ionization fraction, heated fraction, means like the fraction of regions with the temperature more than the CME temperature, mean gas temperature, and I use a mean free path method to characterize the size distribution of, let's say, the emission regions, and characterize the distribution in these two parameters, which is R peak and the full width of at half maxima. This one are the parameters which characterize the distribution which we derive from this mean free path method. Now, talking about this LOFAR results, the upper limits are here, and this is like 1 sigma error bar. So what we do is that we explore our source parameter space, and here I am presenting like 1000 models randomly chosen from this entire set, and trying to see if any model is above this upper limit or not. What we see is that only tiny bit of models are actually above the 1 sigma level, and these models which are presented in color, that has higher probability to be ruled out. Okay, so only like the models which are above, let's say here, these are ruled out, we can say, by 1 sigma level. Now these are like only 5 to 10% in total set which we use. It's not very good at this stage. So for that, what we try to do is study the statistics of this excluded model or disfavored model. Scenario is the same when we go for the other two redshifts. These are redshift 8.3 and 10.1. And when we do a Bayesian analysis, then the results are presented here. So what we found is that the disfavored model, and these are without any radio background or something like that, these are pointing towards very highly patchy reionization scenarios or highly patchy heating scenarios. These are pointing at that disfavored model prefers high emissivity from the sources, high UV emissivity, and their number densities has been very small. That is highlighted by this high value of M bin. This is also true for these X-ray properties, which will lead to very patchy heating scenarios. For example, here I am presenting two slices from two excluded scenarios. Here, the yellow regions are ionized regions and these green regions are neutral regions without any heating. So this is a very patchy ionization scenario, and that will produce a power spectrum which is much larger compared to the upper limit. And this is a scenario which is ruled out. And this is a patchy heating scenario where the yellow regions are now positive signal and this is negative signal. This is also ruled out by this 1 sigma label from loafer. Now, this same Bayesian analysis also put limits on these IgM parameters, and this is more or less 2 sigma level of limits which we derive. What it says is that ruled out models are very much like it will have huge ionized regions or huge emission regions, and those are only set of very extreme models which at this moment can be ruled out. Now, when we also incorporate all possible upper limits, whatever we have from this 21 centimeter observation, what we found is that okay, at redshift 8 it is basically biased by Hera observations, and it is ruling out a model which is this dashed line which present neutral and cold IgM at redshift 8, which is indicating that at redshift 8 IgM has to be heated in some way, right? And this is also been true at redshift 10. This is roughly touching this limit, but it's not I mean possible to rule out at redshift 9, but at redshift 10 it is ruled out. So this scenario is already ruled out at redshift 9. Now, apart from this interferometer based observation, there are observations using single antennas, and for example this AJS, LEDA, SARAS, which are trying to observe the sky average signal as a function of redshift, and it has been shown that several models has been ruled out already. And for example, we use AJS high band data, not the low band. Low band data is the least controversial data, but still using the high band data which doesn't claim a detection, we are able to rule out, for example, a fuzzy dark matter type of model, right? Now, AJS low band data, which is created this controversial brightness temperature profile, which has a very strong signal, and its nature of this profile is also very different compared to what theoretical predictions are. And that deep signal can be only explained introducing excess cooling mechanism or excess radio background. But it is probably that their analysis method was had some error, and it's probably due to some residual unmodeled systematic which led to this particular very strong signal. So this is more or less understanding at this point. Now, apart from that, SK is on the way, and there are huge amount of theoretical studies in terms of let's say imaging topology study, detecting large ionized regions using matte filtering techniques, bispectrum maps, etc., which is giving us very high hope that okay, over down the line in few years, so we will have very good quality of data, and various very precise science can be done with this SK data. And it's already like in a timeline frame, there are already like 4 antennas on ground, and in few years there will be this A2 configuration with 64 antennas, and we will have some data to start exploring. And over few years, of course, we will be able to do much more. Also, there are updates from other observation sites. For example, there are many space-based instruments planned. From India side, there is Pratus planned, and there are already from your side, DARE, DAPPER, and far side been planned. And if that is happening, let's say in 10 years or so, which will give us advantage of let's say avoiding some systematic, and which will lead us to a better achieving let's say the goal in terms of like both power spectra as well in terms of the brightness temperature average quantity. Now with this I will just summarize what I tried to convey here is that this 21 centimeter probe is a very promising, as this is line emission and we can just probe different state of universe at different era. Already the results from LOFAR, HERA and FWA, they are ruling out models and they are progressing very nicely over last few years, and these are moving towards a detection which will probably happen in, let's say in next few years. So there is a huge improvement in understanding the systematic in different team, which is going very nicely. So what I talked about is the inference about the source properties and the IGM properties. What I tried to say is that at redshift 8, 9 and 10, so there are presence of the patchy reionization model and patchy heating model. This is not the scenario at those redshift. Also, these limits are anyway very weak, so most of the models are still valid. And we will be waiting for the, let's say, the upcoming telescopes, and those will provide us very nice information. So this is the hope. So I'll stop and.
Hi, Ru. A very nice talk. So I just wanted to ask, when you calculate power spectrum using your Grizzly simulation, do you also consider the fact that so your IGM is very, very cold, and that will raise the H1 optical depth. So the assumption that optical depth may be small may not be true. So do you consider
so
that?
for this 2025 study, we did that, but in 2020 study, so that was one thing we were using the linear expression for tau. Here only one thing is missing, that we still are not including the light cone effect. So okay. That will be like, okay, taking more time. We are including the resistive phase distortion in our study, but not the light cone effect. Otherwise, the tau thing is incorporated correctly.
Thank you.
In the couple of models you say ruled out, what does it say about the sources at redshift 8 or 7 or something? It tells something about particular sources cannot have some F escape or something, or?
Yeah, so these sources are having like huge emissivity in UV. So in principle, like if you use a luminosity function type of thing, those models are already ruled out from there. But this is like, okay, already towards that line and independently verified by H1 observation.
Okay. Hi, thank you for the very nice talk. I have a naive question. So in the Grizzly, you have two of the inputs are the minimum halo mass for the UV emission and the X-ray emitting halos. So is it ever possible to, from these values, if there is a measurement ever, to pull out the POP3 star mass function or the AGN mass function, or is it too computationally expensive to do it? I know there are other uncertainties that will come in, like escape from this, there are all of these things.
This is possible. So it is our plan, and we are developing a new code, new version of Grizzly named Polar, which is basically tracking all the evolution of, let's say, the halo mass function as well as the luminosity function, all like from the star level. So there, all these things have been done consistently. So there, of course, like the number of models will be ruled out, probably will be less, because here I have the freedom that, okay, I can choose any emissivity, etc., etc. But when we do that, so there will be already a constant from there. But
it's continued. In that case, what is the maximum value of the POP3 mass that you can take? Do you know?
Okay, that hasn't been studied, so
okay.
That we have to check.
Okay, thank you very much. Thanks.